Hello, dear students. We are start our lecture number 16. The theme of our lecture, methods of manufacturing plastic products. Write down to your note the theme of our lecture and the plan of our lecture. 16.1 Polymer materials. 16.2 Formation processes for plastic parts. And 16.3 welding plastics. 16.1 polymer materials. 16.2 formation processes for plastic parts. And 16.3 welding plastics. Write down to your notes these items. And we are start items 16.1 polymer materials. Spline penoplasts have low physical, mechanical, and technological properties, so they are rarely used. In addition to resin composite, phenolics include fillers, hardness, hexamine, calcium, and magnesium oxides, and oils. Powders with various fillers are used for the manufacture of radio engineering parts of electronic equipment, dielectric of complex circuits, housings and covers of devices, complex reinforced and other parts operating at elevated temperature and high humidity. With sheet filler is widely used in radio engineering, Getinax and Textolit. Getinax consists of cellulose paper treated with temperature resin. Getinax has high mechanical strength, relatively low water absorption, and high oil resistance. Products made from it work at ambient temperature from -60 to +70 degrees of Celsius. Textolit. Textolit is a layered pressed material consisting of 2 or more layers of cotton fabric or glass paper impregnated with thermosetting phenol formaldehyde resin. Parts made of Textolit are resistant to vibration loads, wear resistance, and electrical insulating properties. Organosilicon polymer materials. In radio electronics, instrument making, and other branches of technology widely use engineering plastics made on the basis of synthetic organosilicon resins, with mineral fillers. The special features of these materials are arc resistance, heat resistance, chemical resistance, water resistance, and good electrical insulating properties. The long-term operating temperature of products made from them is 200-300 degrees of Celsius, and for some plastics 600-800 degrees for Celsius. Plastics based on silicone resins slightly change their properties at temperature from 60 to 60 to 250 degrees Celsius, and in some cases up to 550 degrees of Celsius. Plastics based on high molecular organosilicon compounds are used for the manufacture of parts for radio, electronic, and electrical equipment and devices. Fiberglass. Fiberglass is a high-strength structural material produced from synthetic resins with glass fillers. The binders are polymers of a linear structure that are capable of forming a three-dimensional structure or are established during the manufacturing process of products. Organosilicon, polyamide, polycarbonate, polyepoxy, and other resins are usually used. Fiberglass does not lose strength at 250 degrees of Celsius, can withstand short-term heating up to 2500 degrees of Celsius and higher. Has got resistance to impact and dynamic loads, and is able to dampen vibrations of structural elements. In radio electronics, they are used for the manufacture of high-strength and heat-resistant products, friction parts of heavily loaded device housing, and also as a high-quality electrical insulating structural material. Fiberglass plastics are divided into fiberglass laminates, glass fiber laminates, and anisotropic fiberglass materials. Fiberglass laminates are layered sheet materials made from panels of glass fabric, impregnated with resin and processed by pressing. Fiberglass materials are made from chopped fiberglass and glass strands and connecting resin. Anisotropic glass fiber materials are produced from oriented glass fiber by laying them in parallel while impregnating them with a binder polymer. Laying fibers in specific directions ensures anisotropy of the mechanical properties of fiberglass while maintaining high values of strength and impact strength. So, have your questions about item 16.1, polymer materials? If you have any questions, please write down it for our Telegram group and for our forum on the course. And we are start item 16.2. 16.2, formation processes for plastic parts. The main methods of manufacturing plastic parts are compression molding, injection molding, blow molding, and vacuum molding. To obtain permanent connections, welding and gluing methods are used. Finishing and fine-tuning of parts, threaded cutting and production of small diameter holes are performed by mechanical cutting. Compression pressing or compression molding. The essence of this method is that the source material is the form of powder, granules, tablets, crumbs, or fibrous mass is loaded into a mold and at elevated temperatures is compressed by a punch, which simultaneously shapes part of the surface of the product. The pressing temperature for thermosetting polymer materials ranges from 140 to 200 degrees of Celsius. Write down to your notes the pressing temperature for thermosetting polymer materials. And for thermoplastics, from 120 to 180 degrees of Celsius. The press material is heated before loading the media into the mold. If products must have metal elements, they installed in a mold before loading press materials. To remove volatile substance and moisture from the press material, immediately after closing the mold, raise the punch for 2-4 seconds. This is repeated 2 or 3 times, after which the press material is finally compressed and kept under pressure for a certain time. Pressure during pressing depends on the fluidity of the polymer material. For pressing products from powdered, tableted granular material, a specific pressing pressure of 20-30 Newton per millimeter square is usually used. For layered plastics, plates, sheets of from 2 to 5 Newton per millimeter square. After holding, the pressure is released and removed from the mold using ejectors. In figure 16.1 shows one of the diagrams of a mold for compression pressing of thermosetting plastic with electrical heating. Pressing is carried out on specialized hydraulic presses. Compression pressing is used to produce parts of simple configuration from thermoplastic and thermoplastic materials. On the figure 16.1, you can see mold for compression molding. Lattice pressing. In contrast to compression, during cast pressing, the source material is brought to plastic state in a separate state to the loading chamber, from which it is squeezed out with a punch at a pressure of 150-200 Newton per millimeter square through the gating system into the forming cavity of the matrix. You can see it on the next figure, on the figure 16.2. In figure 16.2, shows an ejection mold in two positions. The press material is loaded into the loading chamber, heated under pressure to a semi-liquid state and squeezed through the spur hole into the closed working cavity of the matrix. Where it is kept until curing. The product is removed by detaching the mold and using ejectors. Casting pressing has a number of advantages over compression. The resulting products have a more uniform structure, since the press material's softness evenly through the entire volume when extruded through these gating channels. Gradually, heated press materials has good fluidity, which makes it possible to obtain parts with deep holes and different wall thicknesses. The disadvantages are the additional consumptions of material of the gates on the gates and the more complex design of the molds. Next type of molding is injection molding. For injection molding, special ones are used, casting machines, like in figure 16.3, injection molding diagram. You can see one, it's a press matrix, two, it's nozzle, three, heated cylinder, copper with powdered press material, four, and five, plunger. So the polymer material in the form of granules is preliminarily softened in a special heating cylinder of the machine to a state of fluidity. After which it is pushed by a plunger . plunger into the forming cavity of the casting mold. By cooling under a certain pressure, the polymer receives the configuration of the product. Since the shrinkage of the polymer upon cooling is 9 to 10 times greater than the shrinkage of the metal of the mold, the product is easily removed from it. Injection molding is a highly productive and cost-effective method. All operations are maximally automated and controlled by special time relays, through which the time of application of pressure, the holding of the product in the mold during cooling, and the duration of the entire casting cycle are regulated. Automatic casting machines produce 16,000 parts per shift, which is 20-40 times more than which compression of casting. For injection molding, mechanical, pneumatic, hydraulic, semi-automatic or automatic casting machines are used. The injection molding methods produced products of complex configurations with different wall thicknesses, with stiffness threads, etc., from thermoplastic polymer materials. Injection molding is also used to produce parts from thermosetting plastics, but with the use of special casting machines that contain various devices that prevent premature hardening of the material in the gating system before filling the mold. The quality of plastic parts depends on the properties of the processed material, the condition of the tool and the technological molding modes. The surface roughness of parts made by pressing and injection molding generally corresponds to class 7-8 according to the STU. And the accuracy is within the 8-11 classes. To produce pipes, tapes, various profiles, aptly protective sheets to wires, etc., the extraction methods is used, which is continuous extraction of a polymer material in a viscous fluid state through a hole of a certain profile. Continuous extraction is carried out on special machines, extruders, consisting of a hopper for the starting material, a heater cylinder containing a mechanism that provides the necessary extrusion pressure, forming heads with a hole of the desired profile, a device for cooling the resulting product, and component equipment for acceptance. Products extraction of polymer materials or extraction products for polymer materials through the hole in the head can be done with augers or worms, a piston, or rotating disc. In figure 16.4 shows a diagram of a single screw extruder. To obtain pipers of protective coating for cables, a mandrel or wire is passed through the nozzle of the head. On the figure 16.4 scheme of extrusion. 1 auger. Working cylinder, it's position number 2. Bunker, position number 3. Pipes for hot head of steam. Nozzle. Mouthpiece. Most thermoplastics are some thermoses are processed by extrusion. The extrusion method allows you to produce high-quality products continuously, which ensures high productivity, cost effectiveness, ease of control, and automation of production. Next type of forming is pneumatic and vacuum forming. Using these methods, specially shaped parts are obtained from thermoplastic sheets. The part is formed in a heated state in dies. The regulating product is cooled without removing the external force. Figure 16.5 and 16.6. 16.5 and 16.6. So on the figure 16.5, you can see the diagram for vacuum forming. A, it's local heating. B, air suction. And C, pushing out the product. Air, the direction of suction of air. And then pushing product. On the figure 16.6, scheme of pneumatic forming. 1, it's matrix. 2 is product in the process of formation. 3, bottom plate. 4, punch. During blow molding, a thermoplastic sheet preheated to a highly elastic state under the action of compressed air is deformed and pressed against the forming surface of the matrix, acquiring their shape. There are 3 pneumatic formations, like in figure 16.6a. It's 3 pneumatic formation without the punch. Punch, it's 4 on the 16.6b. There are free pneumatic formation 16.6a and directed 16.b. In free forming, the formation of the material occurs only due to the pressure of compressed air. In directional forming, preliminary drawing is carried out by a punch through which compressed air is supplied for final molding of the product. Vacuum forming is carried out as with free pneumatic forming in a matrix without a punch. After heating the sheet located on a matrix, air is sucked out of the matrix cavity. Under the influence of atmospheric pressure, the thermoplastic is pressed into the working cavity of the matrix. The finished part is pushing out with compressed air. Pneumatic and vacuum molding are usually used in the manufacture of thin-walled, large-sized products from organic glass and vinyl plastic. Please have your questions by the item about the item 16.2. If you have a questions, as usual, you can write it to our Telegram group or on our course in the forum, to the forum. Now we start item 16.3, welding plastics. Welding plastics. Permanent connections of parts and workpieces made of thermoplastic polymer materials can be obtained by pressure welding methods to a certain extent similar to the methods used for welding metals. The parts to be welded are heated to a plastic and viscous flow state and compressed with a slight force. Under the conditions, the mobility of macromolecules in the surface layers increases, and as a result of their mutual diffusion, a strong connection is formed. Since the temperature of the viscous current state of thermoplastics is close to the temperature at which their decomposition begins, it is necessary to strictly observe the heating temperature set for each polymer. For organic glass, the heating temperature during welding is 210 plus minus 10 degrees of Celsius. For polystyrene, it's 140 plus minus 10 degrees of Celsius. For vinyl plastic, 230 degrees of Celsius plus minus 10 degrees of Celsius. The degree of destruction of the polymer also depends on the duration of heating. So heating during welding should be short term. Depending on the methods of heating thermoplastics, welding is used with contact head of a heating element, tool. Heated air, high-frequency currents, ultrasound, etc. When welding with a heated joining tool, the workpiece are heated at the joints with a special heated tool and pressed. Heating can be carried out according to two schemes. The first is characterized by the fact that the heater collides directly with the surfaces being welded. After heating, the material to a viscous flowing state, the heater is removed and the workpieces are connected and without removing the pressure cooled. Welding with a heated tool with heat supplied to the surface to be welded is usually carried out but overlap. Butt welding is used to connect workpieces with thickness of from 2 to 20 millimeters. The pressure when joining surfaces of polyethylene and polyamide is 0.15 Newton per millimeter square, and when welding organic glass and polyvinyl chloride is 0.05, 0.1 kilogram foot per millimeters, kilogram force per millimeters, on average, the optimal pressure for most thermoplastics is 0.02 from 0.02 to 0.05 meganewton per square meter. When welding according to the second scheme, the heater tool collides with the outer surface of the product, and heat is transferred to the welding zone through the entire thickness of the workpiece. The tool is massive heater with a constant temperature which simultaneously compressed the parts being welded. Figure 16.7, scheme of welding with a heated tool. This type of welding is used to connect the workpieces and to end with an overlap. Weld organic glass, polystyrene, polyvinyl chloride, polyamide, polyethylene, polypropylene, fluoroplastic, etc. The pressure when welding rigid thermoplastics is 2-3 Newton per millimeter square, and film materials from 0.1 to 0.5 Newton per millimeter square. Welding with heated air or other gas is usually carried out using filler material in the form of a rod made of the same thermoplastic as the parts being welded. The edges for the workpiece to be joined and the filler rod are heated with a stream of hot compressed air from the nozzle of a special welding heater. The filler rod is placed with slight pressure. The base and filler material transform into viscous flow state and form a weld. For such welding, but welds of all types, corner, T-joint, and overlap welds are used. Material up to 2 millimeters thick is butt welded without finishing the edges. Workpieces with a thickness of 5 millimeters and 5 millimeters are welded in accordance with the Y-shaped and X-shaped edge processing. The gas temperature at the outlet of the heater nozzle is set depending on the material being welded and should be from 50 to 100 degrees of Celsius higher than the temperature required to heat the surface being welded. Heated gas welding is used for the manufacture of various shaped parts. Welding with high-frequency currents is usually carried out in a continuous manner. The product to be welded is pulled between rotating rollers, electrodes, to which high-frequency current is supplied from a special generator. 16.8. High-frequency welding scheme. The material is heated to the required temperature and compressed. Welding with a high-frequency currents is used mainly for joining workpieces made of materials where the dielectric loss factor is not less than hundredths of a unit. These include polyvinyl chloride, polyvinyl acetate, polyamides, cellulose ethers, etc. Materials that are good dielectrics, polyethylene, polystyrene, cannot be welded using these methods. They use an ultrasonic welding method. Ultrasonic welding of plastics is similar to welding of metals. Ultrasonic vibrations are applied in the direction of the applied pressure, perpendicular to the surface being welded. Figure 16.9a. Ultrasonic welding diagram or scheme. 1. It's winding. 2. Magnetostrictive transducer. 3. Wave guide. 4. Its product to be welded. And 5. Support. Ultrasonic vibrations are applied in the direction of the applied pressure perpendicular to the surface being welded. Its surface and its ultrasonic pressure. Most of the heating occurs at the junction of the welded surfaces, which eliminates overheating of the material along its thickness and ensures high productivity of the process. Since welding is carried out by one-sided contact with the concentrator, the thickness of the second workpiece can be unlimited. The ultrasonic methods allows you to weld products in hard-to-reach places. Ultrasonic has successfully welded thermoplastics and hardened plastics. The permanent connection of hardened materials is achieved by the chemical interaction of polymers. In polymers in the solid state, chemically active groups are retained, which under certain conditions can directly or through an additionally introduced substance react with active groups of the surface layer of another workpiece. Chemical welding of hard plastic requires intensive heat supply to the surface being joined and intensification of vibrations of polymer molecule units containing reactive groups. Currently, chemical welding methods using high-frequency currents and ultrasound are used. When designing plastic parts, the features of their production technology should be taken into account. To prevent warping and distorting of the part, the cross-section must be the same or similar in thickness, without large local thickenings and thinnings. The difference in the products obtained by pressing should not exceed the ratio of 1:3, and with the cast methods from 1:6. It is necessary to increase the mechanical strength of long and flat parts, for by increasing the cross-sectional area, which leads to an extension of the pressing process and warping of the part after cooling, but by creating stiffness. In this case, sharp transition from one wall thickness to another should be avoided. The stiffness should not form a closed loop. Long parts should not touch the entire mounting surface. The contact surface must be reduced by making projection shoulders or legs. When the holes are completely formed by pressing, it is necessary to provide a slope in the direction of pressing. Plastic parts must have smooth combinations of surfaces, which will simplify the manufacture of the mold, facilitate the pressing process, and prevent the appearance of internal stresses that occur in the outer and inner corners without rounding. The wall thickness in the corners of the part should be slightly greater, about 0.5 to 1.0 millimeters, than the thickness of the matting walls. With a wall thickness of 3-4 millimeters, the required thickening can be obtained by making the same mating radii for the external and internal surfaces. Smooth thickenings of the walls in the corners of parts, such as cases and boxes, significantly increases their mechanical strength. Various protractions on the surfaces of the part should have smooth contours and roundings at the interfaces. As a result of shrinkage during pressing, casting, and other molding methods, plastic parts can exhibit significant variations in size. Their final finishing is done by cutting. Cutting methods are also used to remove sprues, clean bars, holes of small diameters, cut threads, etc. Features of plastic processing are determined by their specific properties. Plastics, with the exception of fiberglasses, have little shear resistance. This would allow them to be processed at higher conditions, but the low thermal conductivity of plastics leads to intense heating of the tool, softening and melting of thermoplastic parts, charring and burning of thermosets. The working surface of the tool is coated with resins, which make it difficult to remove chips and deteriorates the quality of the resulting surface. When processing plastics at low speeds and large cutting depths, cracks and chips appear. When machining plastics, cutting tools made of hard alloys provide the greatest durability and productivity. The rear and front angles are chosen slightly larger than when processing metals. To avoid chips sticking, the grooves for chip removal are polished. To make holes and cut threads, it is necessary to use larger tools. Threads in plastic parts are also obtained by pressing in metal reinforcement and direct pressing using threaded marks and rings. Alt-hood pressing can be used to produce threads of any profile. It is recommended when designing to use a special thread with rounded tips and avoid a rectangular profile due to its reduced strength on sharp edges. So, our lecture for this material is finished. This is the last lecture, lecture number 16. So, if you have the questions about our materials, about this lecture, about item 16.3, you can write it to our Telegram group. You can ask me. and I try to answer all your questions. For today, our lesson is finished. See you on exam, on consultations. See you later. Goodbye. Have a nice day.